So in this video, we are going to continue with CC7, and this time I'm going to focus on metals. As it's CC7, it's a topic that comes up on paper 1 and on paper 2. Previously, we've looked at two different types of bonding. We've looked at ionic bonding, which is between a metal and a non-metal, and we've looked at covalent bonding, which is between two non-metals. We're now going to look at metallic bonding. And before we look at what metallic bonding is, we're just going to talk about what metallic bonding isn't, okay? The common misconception here is that if ionic is metal and non-metal, and covalent is non-metal and non-metal, then metallic must be metal and metal. So two different metals reacting together to form a metallic bond. And that is not the case. That is not what metallic bonding is. So we're just going to have a look at why. When we look at ionic bonding between a metal, here I've got sodium, and a non-metal chlorine, you've got metals that want to lose electrons. In sodium's case, it's got one in its outer shell, so it wants to lose one. And you've got your non-metal that wants to gain an electron. The metal will lose the electron, the non-metal will gain, and both will end up with a full outer shell. So both can end up happy by the metal losing and the non-metal gaining, and that's an ionic bond. When we had two non-metals reacting together, so I've used two chlorine atoms in this case, I've got two atoms that both want to gain an electron, and in order to both end up with a full outer shell, they instead share electrons. So two non-metals can react together because they can share. A metal and a non-metal can react together because the metal will transfer its electrons to the non-metal. However, when you put two metals side by side, so for example, I've got sodium, which is in group 1, and I've got calcium, which is in group 2. Sodium has got one electron, so wants to lose one. Calcium's got two in its outer shell, so wants to lose two. But if you've got two atoms that both want to lose electrons, and neither of them want to gain electrons, then they cannot react and they cannot make each other happy. Those electrons can't just disappear. If they both want to lose, but neither of them want to gain, well, then those electrons have nowhere to go. So metals, different metals, are not going to react with each other because they can't both end up with full outer shells by reacting together. So metallic bonding is not the bonding between two different metals. Sodium is not going to react with calcium. Potassium's not going to react with lithium. Okay, they're not going to react with each other because they can't both end up with full outer shells. So metallic bonding is not the bonding between two different metals. Then what exactly is metallic bonding? So if we look here, I have drawn out a diagram. And in my diagram, I have just got sodium atoms. So if I had a piece of sodium, that piece of pure sodium would be made up of sodium atoms. And because sodium's in group 1, all sodium atoms have one electron in their outer shell. Now, as we've described before, sodium wants to lose an electron to get a full outer shell. And that is going to happen. Your sodium atoms are going to lose electrons. They're going to lose that outer shell electron so that they've got a full outer shell. And when they lose that electron, they will end up with a positive charge. But, as I said above, the electrons can't just disappear. And if I've just got sodium by itself and it's got nothing to react with, then there's nothing to accept those electrons. So what will happen is the electrons that the sodium atoms lose don't actually leave the piece of sodium metal. Instead, those electrons that the sodium atoms lose stay within the piece of metal and can move freely around the piece of metal. Electrons are all negatively charged, so what you end up with is you end up with positive ions because the sodium atoms have all lost one electron, and then you get those negative electrons with nowhere to go, so they stay within the piece of metal and they move around freely. Electrons are negatively charged, and because they can move around freely, we say they are delocalized. So what you end up with is positive ions and negative electrons that are then attracted to each other. Okay, so these positive ions would all repel each other because they have the same charge, but because you've got those negative electrons in between, overall you get an attraction between the positive ions and the negative electrons, and that holds the metal together. So in any metal, if you had calcium, you're going to have all of your calcium atoms losing 2 electrons. Those electrons have nowhere to go, so they stay within the piece of calcium metal, and then you have an attraction between those negative electrons and the positive ions. That's going to happen in every metal. If you had a big piece of gold, all of your gold atoms will lose electrons. Those electrons will stay within the piece of gold, and you'll have an attraction between the positive gold ions and the negative electrons. So metallic bonding then, they're the bonds that hold a metal together. In a piece of gold, it's the bonds that hold the golds together. In a piece of sodium, it's the bonds that hold the sodium together. However, this definition here is not going to get you any marks. Just like if you were asked what is an ionic bond and you said the bond between a metal and a non-metal, that doesn't get you the marks. With metallic bonding, what you actually need to say is that it's the electrostatic force between the positive metal ions and the negative delocalized electrons. So we've come across this word electrostatic force before when we looked at ionic bonding. Electrostatic force can be used to describe any attraction between something positive and something negative. And here, the positive is your positive ions, and what's negative is your delocalized electrons. You get this electrostatic force between positive metal ions and the negative delocalized electrons. And that's what a metallic bond is. The bonds holding a metal together, but more specifically, this is going to be your definition. Just like what we had in ionic structures, where we said that the structure was giant, again, in metallic structure, the structure is also going to be giant. Before we had giant ionic lattice, now we've got giant metallic lattice. So in one piece of sodium metal, you're going to have billions of sodium ions, and you're going to have billions of negative delocalized electrons floating around. So it forms a giant metallic lattice. We saw with ionic bonding that the electrostatic force was strong. That is also true in metallic bonding. That force between the positive metal ions and the negative electrons is incredibly strong. Because that force is strong, it requires a lot of energy to overcome, and metals are going to have high melting and boiling points. They're going to be solid at room temperature, okay? That's something we should already know. Metals are solid at room temperature. If they're solids at room temperature, it means there's a strong attraction between the particles, and a lot of energy would be required to overcome it. The other property of metals that you need to know is that they can conduct electricity. So when we looked at conducting electricity, we said that you need charged particles that can move freely. In metallic bonding, you've got 2 types of charged particles. You've got your positive ions and you've got your negative electrons. But to conduct electricity, your charged particles must be able to move freely. The positive ions, because your metal is a solid, these particles can only vibrate. They cannot move freely. But your negative electrons, because we say they are delocalized, they can move freely. So the presence of the delocalized electrons allows metals to conduct electricity just like it did in graphite. So if we look at some worked examples of questions on metals, describe the structuring and bonding of copper. So copper is a metal. So you would talk about the positive metal ions being attracted to the negative delocalized electron by the electrostatic force of attraction. And this is a giant metallic lattice. So they could ask you that question about any metal, and this would be your answer. If they ask you why metals have a high melting or boiling point, they could say, why does iron have a high melting point? Or they could say, why is calcium a solid at room temperature? Anything along those lines. You're going to write out pretty much the same answer of what you've got above, but you're also going to mention that a lot of energy will be required to overcome this force. You're always going to talk about energy when you're talking about melting and boiling points. The next question here I've got is about copper being used for wires. Why would copper be used for wires? Well, if you want it to be used for electrical wires, it needs to be able to conduct electricity. So I'd say copper can conduct electricity because it's got delocalized electrons that can carry current through the structure. I've also mentioned that for wires, it's useful to have a high melting point. You want it to be a solid, and the reason it has a high melting point is because of that strong electrostatic attraction. The other property that we would have learned about metals way back in Key Stage 3 is that metals are malleable, and that means they can be hammered into shape. And the reason they can be hammered into different shapes, if you look at this diagram here, I've got all of my positive metal ions in nice neat rows, and these layers are capable of sliding over one another. And because those layers can slide over one another, we say that they are malleable or they can be hammered into shape. So if you apply a force to the metal, because those layers are in nice neat rows, they will slide over each other. It makes your metal malleable. So that last question I asked there was, why can metals be hammered into shape? Metals are malleable because of the layers of cations that they can then slide over each other. So the typical questions you're going to get about metals. Remember, metallic bonding is just the bonds holding a metal together. It's not between two different metals. I'm going to put two questions on the screen, which I want you to, so this brings in pretty much everything that we've looked at in the last couple of videos. Question 6 and question 7. So in both cases, you're given a table and you're given information, melting points, boiling points, whether or not they conduct electricity. And in question 6, you're asked to identify the type of structure and bonding. Is it simple? Is it giant? Is it ionic? Is it metallic? Using the information that you've been given. And then in question 7, you're given 4 different substances and you are asked to match the substance to its properties. So again, if I was doing this, the first thing I would do was establish what type of structure and bonding that I've got in each of these 4 substances, and then try and link it to the information below. So press pause and have a go with that one for yourself, and then press play when you're ready to go through the answers. Okay, we'll go through the answers to these. Okay, so the first one, if I look at it, it says it has a very low melting point, minus 107 degrees Celsius. If it's got a low melting point, then it's going to be a liquid at room, actually it's got a boiling point of 13, so it's going to be a gas at room temperature. And if it's a gas at room temperature, that tells you that particles are really far apart. That tells you that there's not a strong attraction between the particles. There must be a weak force between the particles. The only weak force we've learned about is weak intermolecular forces, and weak intermolecular forces occur when you've got a simple molecule. So I'm just going to write SM there for simple molecule. You must have a simple molecule if the melting and boiling point are that low, because it's a liquid or gas at room temperature. The next one, I've got really high melting and boiling points, so it must be really strong forces. So we've learned about 3 types of strong forces. Metallic bonds are strong, ionic bonds are strong, covalent bonds are strong. So just looking at the melting and boiling point in this case isn't enough to tell me which type of structure and bonding it is. So then I go further and I look at conducting electricity. And I see that it doesn't conduct when solid and it doesn't conduct when liquid. And that if it's not conducting electricity at all, that tells me that there are no charged particles at all. In ionic bonding, I have charged particles. I've got ions. In metallic bonding, I've got charged particles. I've got delocalized electrons. But in giant covalent structures, I don't have any charged particles. Giant covalent structures don't conduct electricity. So I'm going to write down GC. Now, with giant covalent, you may be thinking, but oh, graphite is giant covalent, and it does conduct electricity. And yes, you're right, it does. But graphite is an exception, okay? Diamond is the typical giant covalent structure that doesn't conduct electricity. Graphite is an exception. So in general, if you're told it's not conducting electricity at all, and it's got a really high melting point, it's gonna be giant covalent. The next one I look at, again, also has a high melting point, also has a high boiling point, so I know the bonds must be strong, so I need to go and look at the conducting electricity. It doesn't conduct when it's solid, but it does conduct when it's liquid. So this tells me that it does have some sort of charged particles, but that they're not free to move when it's solid, but they are free to move when it's a liquid. So that's true for an ionic compound. I'm just going to write an I there. Ionic compounds don't conduct when solid because the particles can only vibrate in a solid, but they do conduct when liquid. Next up, I've got 6 as a melting point. That's very low, and 80 as a boiling point. I mean, that is relatively low if you compare it with what we've got above. So again, this is suggesting to me straight away with those kind of melting and boiling points that it's going to have weak forces, that it's going to be a simple molecule. And then if I look at the conducting electricity, again, it's saying it doesn't conduct electricity, which is also true of a simple molecule as they do not have any charged particles. Okay, if you look at the top row, which is filled in for you, this was for a metal, really high melting and boiling point, does conduct when solid and liquid because those delocalized electrons can move even when it's a solid, and that would have been metallic. Okay, if we look at the next table, this is slightly different. In this one, they're giving you 4 different substances and they want you to match them up. Okay, so the first thing I would do here is sodium chloride, all right? I've got a metal and I've got a non-metal. So I know here that I've got an ionic substance. So I'm going to put an I next to that one. The next one is aluminium metal. It's just aluminium by itself. A metal by itself is going to be metallic. Then I've got diamond, just containing carbon. Diamond is your example of something that is giant covalent. And then I've got carbon chloride. Carbon is a non-metal. Chlorine is a non-metal. And I've got them a known number of atoms. I've got 1 carbon, I've got 4 chlorines, a known number of atoms. That makes carbon chloride a simple molecule. So now that I know what type of structure and bonding I have, I should be able to match those substances to the properties below. If I look at the first one, I do have a high melting point, 660, and I do have a high boiling point. So straight away, I know that those forces must be strong, and I know it's not going to be a simple molecule. Then I look at the conducting electricity, and it conducts when solid, and it conducts when liquid. That tells me that there's always charged particles that are free to move, and if that's the case, then A must be a metal, and that means A must be aluminium. If I look at B, I've got a really low melting point and a relatively low boiling point. That tells me weak forces. If it's weak forces, the only weak force we've learned about is intermolecular forces, which occur in simple molecules. So 2 must be CCl4. Sorry, that says CCl4. Then I move on to C. Again, high melting and boiling point tells me I've got strong forces. It doesn't conduct when it's a solid, but it does conduct when it's liquid. That tells me it does have charged particles, but they can only move freely in a liquid, and that is true of ionic compounds. So C must be NaCl. And then I've got D, really high melting and boiling point. So you can see, even compared to your metals and your ionic compounds, that the melting points of the last one is so much higher, and they never conduct electricity. And that is going to be true of diamond, your giant covalent compound, diamond, which has a really high melting point and boiling point and never conducts electricity, as it does not have free moving charged particles.